is to remove, or remove the wrong word, to alter the variables of integration from essentially x, y to r and theta. So we're going to look at a situation where essentially what we're doing is we're trying to, I'm having issues with little windows all over the place. Try to take an integral that might be quite difficult to do if you stick to the xy world, and it's some region R, and you convert it into the polar world. Now, x's are r cosine theta, y's are r sine theta. That's what this is telling you. It's basically saying all the x's and y's that you've got here, turn the x's into r cosine theta and the y into r sine thetas. And the dx dy, turn that into r dr d theta. Notice it's dead easy to miss that. R dr d theta. Not dr d theta, but r dr d theta, right? An extra r. And that's part of the process. And a couple of useful ones. X squared plus y squared equals r squared is really helpful. So if you ever see that, just replace it. That's just overemphasis. And this is it. So here's question 1, 4x squared y dA. And we're being asked to integrate this over a double integral, over a disk. I don't know why they call it a disk. I would call it half a circle, but who cares? The d is the top half, so it's that, and radius is 4. So that's our region. Right, so I need to figure out how to describe this region in terms of polar. Well, the radius goes from 0 to 4. And wouldn't theta go 0 and then it'd finish over here at pi? So are we happy about the limits of integration of how this region is described using polar? 0 to 4 basically fills in the disk. If you just did 4, all you'd get would be the line, right? But if you do 0 to 4, you're filling in the whole thing. Now, 4x squared becomes 4 r cos thetas squared multiplied by r sin theta. The dA becomes r dr d theta. So far, so good. So what I'm now going to do is just a little bit of tidying up, and then we'll figure out how we're going to integrate this thing. Four r squared cos squared r sin theta. There's another r, so I guess it's r squared sin theta dr d theta. Guess I could do a little bit more before I'm ready. Four r to the 4 cos squared theta sin theta dr d theta. So after, I don't know, 2 or 3 lines of algebra, you should be looking at this fella. So here's a couple of tricks of the trade. These are variable separable. Aren't the limits of integration numbers? What that means is I can separate this question into 2 separate, distinct integrals. That guy. That guy. And we used that trick a couple of times, so last week sometime. Whereas the x's and y's are totally separable, and the limits of integration are numbers. So both those things have to be true. But if they are true, you can separate your integrals out. And what that basically does is it reduces your workload. That's the only advantage, right? Now, won't this guy be a classic Calc 2 question, a power rule? So add 1 to the power and divide by the new power and evaluate it that at r equals 0 to r equals 4. Plug in 4, you go, oh God in Himmel. 4, 16, 64, 256. 256, 1,024. 4,096 fifths. And if that's not right, will you pretend it is?
That's
Nah,
right.
I did that right.
Yeah.
And I can't do 2/3 times 5 right.
That's hard.
God in Himmel, I'm getting lucky. Okay, this fella here is a different problem. We actually have to work on this. What technique from Calc 2 will I use to solve this integral?
That's a U sub in the
Correct. Who's the U sub?
cosine.
Right. So it's a U sub with a cosine, right? U equals cosine theta. Now, since I am a little bit pushed for time, can we pretend that I already know how to do it, which I do, and you end up with that guy, which then becomes check this out. Use cosine negative. Yep, got that guy. That guy is not our fella. I haven't done the integral part. Now I've done them. That's what you will eventually get. Negative 1/3 cos cubed. So when you just trust me on that, you can fill it in. Right. Plug in pi. Negative 1/3 cosine of pi cubed essentially. Take away a takeaway, so it's add 1/3 cosine of 0 cubed times this ridiculous fraction. Okay, cosine of pi is -1. -1 cubed is -1. That's -1. So what do you get? After all that hard work, you just get 2/3. And 8,192 fifteenths. And would you believe it? That is actually the right answer. Because I have the answer grid. The moral of that story, I could easily talk myself out of that. Would you agree if this was us doing this? Wouldn't you think, nah, just ugly. Can't be that ugly. I must have screwed up in my number crunching somewhere. But go figure, it's the right answer. I got really lucky, I guess. Right, before I move on, are we comfortable at this process, which is basically, here's an integral with x's and y's. We're going to turn all the x's and y's into r cosine thetas and r sine thetas. We're going to turn the dx dy into this. We're going to look at the region and describe it in terms of polar values. And then after that, it's a whole load of integration fun. That was a lot of work. This next one is integral over a region R, 2x take away y dA. And the region that we're trying to do, oops, got some people coming in. The region we're trying to do it over is a bit messy. It's this guy with an x equals 0 and a y equals x. Okay. I'm only going to take this question kind of halfway through, and then the rest you can figure it out. So let's figure out what this region looks like. That's basically the whole circle. If you do x equals 0, then aren't you doing the y-axis? If you then add onto that the line y equals x going this way, you're essentially getting this piece of cheese. So we have to...
Did someone say cheese?
Yes. Someone did say cheese. So if you take this shaded region, we have to describe this in terms of polar. Well, if you think about how you would create this using the r and the theta, the r is probably the easy bit. If it's a circle, you just go from 0 to the number. So it's 0 to 5. That'll take care of the, you know, any piece of a circle. Now the theta in this case, what angle gets generated here?
That's pi over 4.
And won't you agree that this is a half pi? So can you see that this is the way that that region is described in polar? So our integral is going to be going theta equals pi upon 4 to pi upon 2. R is going to go 0 to 5. 2x is just going to become 2 r cos theta. Take away y is going to be minus r sine theta. And then I'm going to have an r dr d theta. A little bit messy, but that's what I've got. So it's going to go theta equals pi upon 4 to theta equals pi upon 2. R equals 0 to 5. If I pull this r out as a common factor, I've got r squared, 2 cosine theta, take away sine theta, and that r gets that r, that's why it's an r squared. And then I can do dr d theta. Do you see that we got lucky again because the limits of integration are still numbers? Do you also notice that these are variable separable the way I've factored it out? So I should be able to split this up. As that guy and that guy. And that's where dot dot dot's going to happen. Any questions about this process, at least as far as we've gone? You really do need to draw that picture. James?
I was wondering how you got the r squared instead of 2r.
Well, where are we? See this 2r and this r? I pulled this out as a common factor, so that's why that's left. And this other r with that r gave me the r squared. So I just kind of did 2 lines at once. I pulled out an r as a common factor and then multiplied it by this r, and that's where the r squared came from. And when you pull out the common factor of r, this is what's left in the other piece. You can't pull out 2r as a common factor because that doesn't have a 2. Oh, I'm pointing at things you can't see, sorry. This is the r, this is the common factor r. Put them together, r squared. Pull out the common factor of r, that's the other piece.
Oh, I completely dropped that. I was writing too fast to catch up, and that was a 2 cosine theta.
Yes.
I just
We
had
good?
to. Yeah,
Right.
we're good. We're good.
Very good. And we're happy about the dot 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 once you get to here. Now, do not do this split if any of these limits of integration have variables in them. And so I can get this out of my head. You know it is theta, not theta. Got that? Theta. Z, theta. You know, things like that. I don't know how the Americans managed to screw up Greek letters of the alphabet. How you even managed to say them different. That's just being awkward. I think that's what that is. This is just one I'm making up. Suppose that you have a double integral of r and you're being asked to find this guy. And r is described as a donut. It's actually called a torus. And that's 4, and that's 2. Now you want to describe this shape in terms of theta, oops, and in terms of r. It goes from 2 to 4, and it goes from 0 to 2 pi. So that's what that shape would look like, right, if that was r. Suppose r was not that shape, but this shape. Good happen. R would still go from 2 to 4. What would be the theta in this shape?
0 to pi.
Now, could you imagine, oh God, I'll not do the last one, but can you imagine it could be that size, right? Do you notice that the R doesn't change? Wouldn't that just be a matter of choosing pi to 2, well, I'm saying pi, half pi to 3/2 pi. So you need to adjust your angles a lot. Now, in this fella here, the double integral is going to change. E to that guy becomes e to the r squared. Then you get an r, a dr d theta. And r is going to go from, what, 2 to 4. And theta is going to go from 0 to 2 pi, because we'll pretend that's the one that the question was. Now, in this question here, they can be split. If there is only one variable, it's variable separable. Do you notice that I just brought 1 as a d theta out? This fella here is dead easy to do, right? He ends up being 2 pi at the end. What method will I use to integrate something like r e to the power of r squared?
U sub.
Yep, correct. What u sub?
U is equal to r squared.
Right. I think if you do that, it ends up being a half e to the u, and then off you go and do what you need to do. This is a version of 4. We're doing this guy. And D is described as a semicircle with equation x equals 64 take away y squared and the y-axis. So I'm just going to get this one set up. Okay, semicircle, that means half a circle. Doesn't look like the equation of a circle, but it must be, or they wouldn't have called it a semicircle. So I need to figure out, what does that look like in a form that's going to make it easy for me to tell what's going on? Well, if we start off with this guy, if you square both sides, and then you add a y squared to both sides, do you see it's a disguised circle? Not only do I know it's a disguised circle, don't I also now know the radius is a? Now they talk about a semicircle and the y-axis. So if you do the y-axis, you're basically doing this guy. And the fact that it was written this way tells me that it's a positive side or the right-hand side. So that is the D that they're talking about. Now the R values, I'm doing them first because they're pretty easy. and the theta value is not. I want to describe starting here like a clock and going anti-clockwise here. So I point at 6 and I finish up at 12, right? What?
Negative pi over 2 to pi over 2.
That's the trick. Because sometimes you get caught up by thinking it's just various versions of, 0 pi, half pi, 3/2, and 2/2 pi, 2 pi. It's not always. Can you see that there can be circumstances where you need to think of negative angles as well as positive? So when you set this fella up, it's going to be theta is negative pi over 2 to theta is positive pi over 2. R goes from 0 to 8. Okay, what is that fella going to look like in terms of R or theta or both?
Would that be negative r squared?
Yep. And then you're going to have an R, dr, d theta. Is this a variable separable situation? In fact, isn't it just another one of those where the theta gets the number 1?
It's just like the last problem, except the r squared is negative.
Pretty much. So that's going to be a U sub, and off you go and do what you need to do. 2 thumbs up, looking good. Any questions before I move on? Let's have a D. Let's have the sine of square root of x squared plus y squared dx dy, and db circle radius 4. Right, that one's almost a non-starter. Would you agree it's easy to do a whole circle? Right, so it's going to be theta is 0 to 2 pi. Oh, this circle has a radius of 4, so from 0 to 4. Okay, what will the sine of the square root of x squared plus y squared become in terms of r or theta or both?
It'll be sine of r.
And then won't we have an r dr d theta?
Professor, I think Abigail needs to be let back in.
Oh, thank you for telling me. I'll nip in and let her in. Sorry, Abigail, I don't get to see, when I go on the white screen, I don't actually get to see much except your faces. And that's not much fun, I can tell you. Oh, I got that one in really good. Did you like that one, James? Oh, James has disappeared. Okay, this is a variable separable situation. And I'm just pulling out a 1. And that way I can do that guy. And that way I can now focus on this fella. Calc 2 technique. It is not a U sub. If that was r squared, it would be, but it's not. So it's not a U sub. What method?
Integration by parts.
Yeah. So, yeah, the vast majority of situations that we've came across haven't they been U subs, just the way they are. But always be aware that there is the now and again. Here's one of the now and agains, where integration by parts is going to be your go-to guy. We cool on that? Okay, we're now going to do excuse me, we're going to do a one-off special case, and this is question 6. we're going to look at the area of one loop of 6 cosine of 3 theta. And you might say, well, how can we do that? Because double integrals calculate volumes, they don't calculate areas. But technically, if you do a double integral of 1, so it's 1 unit high, won't the volume be the same as the area? So that's how we get around that. Now, if I want to find out what 6 cosine thingy-bob is, which I really need to, I guess, it looks like this, or at least one loop of it does. And this angle here and this angle here is important. This angle here is, I believe, pi over 3, and this angle here is negative pi upon 3. And you might say, well, how do I know that? I simply just find out when 6 cosine r theta is 0 and solve for theta. Okay, just trust me on that. Okay, so, oh, the r value. Oh. If you want to fill this shape up, doesn't r go from 0 to the edge of that loop? So that means that theta goes from negative pi upon 3 to pi upon 3. R goes from 0, but not to a fixed number, but to this fella. And then we do r dr d theta. You still with me? Cool. So, integrate this fella, you will get 1/2 r squared. You're going to evaluate it at 0 and at 6 cosine of 3 theta. D theta. And then you're going to go from negative pi upon 3 to positive pi upon 3. So it's now going to be the integral of 1/2 times this guy squared is 18 cos squared 3 thetas, take away nothing. So now you're going to have to find that guy. Okay, give me a Calc 2 technique. And it's not a U-sub or an integration by parts.
Half angle identity.
Yep. So turn cos squared 3 theta into 1/2 brackets 1 plus the cosine of 6 theta, double 3. Multiply it out, and it's one really ugly mess, but it does come out at the end. Next one, question 7, or like it at least. This is the surface. They describe it as under this region and above this fella. But that's just vocabulary. That is basically your function x, y, and this is your region D. So to get this volume, you're going to do the integral over region D of x squared plus y squared, the usual dx dy. Polar form, do you recognize this guy? I don't really need a picture. Isn't this a complete circle, 0 to 2 pi, r equals 0 to 7? So I'm going to go theta equals 0 to 2 pi, r equals 0 to 7, won't this guy become r squared? And won't this guy become r dr d theta? And this one is a variable separable. R cubed, 0 to 7, 1 d theta from here to here. Now I'm going to keep that question for a minute. Imagine that the region wasn't this. Imagine the region was that. So basically a donut, right? Pretty straightforward. That stays put. How would you adapt this to cope with that?
The radius would be from 3 to 7.
Agreed. Now let's make it worse. Suppose this region was this donut shape, but only the donut shape that was above the x-axis. So basically, that piece, right? How would we adapt this to cope with the new region?
Do it from 0 to pi.
So do you see that the math is very, very similar? The structure is very, very similar. If this is the only thing that changes, don't you basically just adapt? Maybe you have to change a start and finish R value. Maybe you have to change a start and finish theta value. This process really is designed, isn't it, when the region is a circle, circular, bits of circles, whatever you want to talk about, pieces of cheese shapes, those kind of shapes, this is the go-to guy. If the region you're doing is rectangles, x squares under y cubes, so that kind of stuff, this is not the road to go, because creating this will be horrendous. But as long as it's circular, for want of a better word, isn't this just a matter of choices for r's and thetas for the most part? Any questions about that? Okay. Number 9. We have a plane, 2x plus y plus z equals 6, and it's a disk called x squared plus y squared less than or equal to 1. I don't think I need to draw a picture for a disk. I'd call it a circle, but whatever. Right? Is it not just going to be 0 to 2 pi, r equals 0 to 1? Great. Now, this is an issue. I need a function f of xy, right? If you look at our generic double integral that we deal with, it looks like that, right? The information has not really been given in the format that I need. But if I rearrange this, can you see I now have my z? So I'm going to do a region from 0 to 2 pi, from 0 to 1, 6, take away 2r cos theta, take away r sin theta, r dr d theta. Let's see if you can see all the pieces here. That guy became r dr d theta. This fella gets rearranged as 6, take away 2 x's, you see the x's are r cos thetas, minus a y, which is r sin theta. Is this variable separable? No, just isn't, right? But it is doable, isn't it? So maybe I'll take it just one more step then and leave it. This R becomes part of the question. So it should be called 6R, 2R squared cos theta minus R squared sine theta, dr d theta. Okay, now I can do the step I was going to do. This fella is power rule. This fella is power rule. And so is this fella, power rule. So far, so good. Power rule, power rule, power rule. Right. The cosines and sines are just constants. Now, if you plug in 1, you get 3. Take away 2/3 cosine theta minus 1/3 sine of theta. You put in 0, you don't get anything. Bingo. Would you agree we're just down to a normal calc to integral and using sines and cosines? Nothing too special. Now, I know I'm shooting through quite a lot of these quickly. Hopefully when you look at the video, you can pause on any of the ones that I was just too fast for you. But we're trying to give you as many flavors of how this works. Different situations, different combinations, interactions. So I'm about to move on. Are we good? Got no thumbs up, so I'm moving on. In this case, we're being asked to find the volume. They describe it as inside a sphere. And then outside, so that's inside a sphere. And outside a cylinder. So this is a new question. Now, I'm pretty sure I'm going to make this a total mess. If I had time, I would actually put these in to Desmos and you could see the shape, but here goes anyway. Can you imagine that's the sphere they're talking about? Its radius is 4. And then inside this sphere, somebody has essentially bored a cylindrical hole. Now, we're being asked to find what the volume of the material that's left behind is. So that's the story. Well, you might think, oh, it's dead easy. I'll just find the volume of a sphere, the volume of a cylinder, and I'll subtract the 2. That would not actually give you the right answer. And the reason for that is, isn't there a little curved part of the sphere that gets destroyed as the cylinder shoots through it? And so that subtraction technique that you were going to doesn't account for that, which makes this a little bit more subtle than you think. First problem we've got is, what is the region in the bottom, right? So I'm going straight into polar here. We're going to take this situation and we are going to try, as best we can anyway, figure out what would that shape look like if you stared at it from above, if you were looking at it this way, right? What would you see on the floor? Because that's going to be the D region, right? You know, the D guy that goes here. with a little bit of imagination, won't you see a donut? Won't that be the cylinder? And won't that be what a sphere looks like if you stare at it from the bottom? Wouldn't that be its shadow? So on the inside, we're looking for a radius of 2, and on the outside, we're looking for a 4. So that is how I figured out that part. Now, would you agree that theta is 0 to 2 pi? So this fella is going to be a 0 to 2 pi guy. And this fella here is going to be from a 2 to a 4 guy. So far, so good. Now, don't I need this fella, r dr d theta? Don't I need a z that is in terms of x and y? The only z in town is this guy, isn't it? If you rearrange this guy, isn't that what z squared is? So won't z be the square root of that guy? And now that I've written them that way, I realized that I should have done one more line. I can fix it. Doesn't this need to be in terms of r and or theta? How could you write that down in terms of r?
It'd be 16 minus r squared, right?
Yeah, and I'm going to stick this r at the front. Is this a variable separable situation? So 0 to 2 pi with a 1. What technique am I going to use to integrate this fella?
You said
Who's the u sub going to be?
16 minus r squared.
And you're done. Agreed? Well, that's easy, isn't that? Just going to be 2 pi when you're finished. Now, one of the big problems for this question is the way this is phrased, you need a d, right? You need a region on the floor that's going to be used as your integration region, right? The d guy. And the way this looks, what's the d, right? What's the region? And when you have a situation like that, think of flying above the object and looking at the shadow on the ground, the xy plane's the ground. And can you see whole sphere? That's how you found d. Right. Can you imagine there was a cone with a cylinder cut through it? Right? Wouldn't the outside be the base of the cone? And the inside would be a circle. So you'd have big circle inside little circle, right? Little circle inside big, for example. So, are we good? Whew, a lot to take in. Let's take attendance. So say hi for a few minutes, a few seconds. And our last question for today says, evaluate this integral. Oh, and by the way, I got these the wrong way around. That's y first, x second, right? Evaluate this integral by turning into a polar form. So let me add some stuff. X equals 0 to x equals 3, y equals 0 to y equals 9 minus x squared. e to the negative x squared minus y squared dy by dx. That's actually how I would have written this question. These limits of integration are describing d. So let's see if I can draw what that looks like. X is going to go from 0 to 3. Y is going to go from 0 to this guy. Do you recognize that this guy is actually a circle if you rearrange it? And is it in a circle x squared plus y squared is 9? So isn't it that guy? And if you do y equals 0, aren't you starting at the bottom, right? And go to the top. So what we have just discovered is that this represents that. 0 to 3, oops. Caught myself in time. It represents this little piece here, right? 0 to 3, right-hand corner. So that gives me 0 to 3 on the r's and 0 to pi upon 2. I've made myself clear. That's the region, right? So it's going to be theta equals 0 to only pi upon 2, because it's only 1/4 of a circle. The r going from 0 to the radius, which is 3. E to this fella is negative r squared. Won't this become r dr d theta? So this is the original integral. Do you see I've now converted into its polar version? If I asked you to integrate this one, actually you wouldn't be able to, because what's the there is no antiderivative that works. On the other hand, can't you do this one with a u sub and it's variable separable as well? So from impossible double integral converted into polar, it's now a doable answer and you'll get the result. Question, Ben? No? Yeah. It looks like you had a question. Maybe you didn't. No questions. Well, well done for hanging in there. We learned some cool stuff. We did some smooth algebra, and I made very few mistakes. So I am on a roll today. I'm on a Kaiser roll, I think. Later on, I'm going to say bye-bye. I'll see you all tomorrow, where we'll finish these off and start the next section. Bye-bye, James. Is that you, Abigail, making noises? Are you saying bye-bye?
Oh, yeah, maybe. My bad. I was trying to get my stuff to click.
Okay. Bye-bye. Bye-bye, Jacob. I'll leave you.